Hey there. I'm just going to go through the pitch for my project, and as you can hopefully see on the screen, I've got an autonomous lawnmower. I guess the use case for this is like autonomous lawnmowers at the moment aren't really truly autonomous. They typically use like a magnetic strip or something similar to outline the boundaries of whatever area they're trying to mow. Um, so this is like inherently limited because you can't, well, for one, Wi-Fi connections are needed to make this thing work, and also um, the wire itself, right? Like if you've got a very huge area like farmland or whatever, the wire itself has to be enormous and able to like run the perimeter of that area. So this is like inherently different type of system in the sense that it doesn't rely on a wire. It builds a map of a location, and so it uses LiDAR to build a map of a location, and then it uses a camera to uses LiDAR to navigate that map. And if there's some local disturbance in the map, like a person gets in the way or an animal or whatever, a camera picks up, does object detection on that person locally, and the nav stack picks up there's a person in the way, and the mower moves around that, like does obstacle avoidance around that person and continues mowing the actual map. So that's sort of the use case, right? Like um, there's a mower, it can move around and cut the grass, and it doesn't run over my dog. So the next thing is this. So the first step, like before I could build this thing on the right of this slide, is to figure out how this thing's going to work, right? And the way I did it, or am doing it, is what's on the screen. So there's a drive system that is controlling the wheels. There's a cutting blade that is totally separate from the Raspberry Pi, just for safety reasons. I didn't really want to be driving that cutting blade. There's too many variables, and I don't have enough sensors and time to write sensor libraries to pick up forces on the cutting blade, if the cutting blade's stalling, if we've hit something, blah blah blah. So right now it's on a mechanical switch, um, like a solenoid. Um, And yeah, so that's the cutting blade. The rest of the system though is totally linked back to the Raspberry Pi. So the Raspberry Pi is like the brain of this system. And as you can see on the screen, it's taking information from LiDAR, from an RGB camera, and also from an Arduino. The Arduino is connected to the drive system, and the drive system basically is four 12-volt motors, two of which, one on each side, left and right, have encoders attached. So we can pick up like counts from the encoders and sort of figure out wheel positions, and hence sort of pick up locations. This doesn't work perfectly, right? Because the ground is lawn. So if it skids or it skips or anything happens, we've lost some of that information about um, the encoder position. Is not one like exactly mapping the location of the mower because the wheels skipped around. So we've got more counts than we have rotation. So anyways, this is sort of the overarching thing, right? The Arduino is totally handling the encoder sensing and also the drive. So it's doing pulse width modulation on the 12-volt motors, so it can reverse the direction of either side of the mower, and it can slow down and speed up, and you know, do all the things you'd expect a autonomous mower to be able to do, or autonomous like drive system. So it can vary the speed, it can vary the direction, and it picks up the counts from the encoders on the motors. Yeah, so like I said before, the 2D LiDAR is handling like building a map of like it's sort of like the global map. RGB camera is handling like disturbances in the map, like if there's some obstacle to avoid. So it's just checking for, in this case, very simple, looks forwards. And if it's going to run over something, it doesn't. It stops and does its best to navigate around. You'll also see on there's a controller. So that's like a PlayStation controller that's linked to the Raspberry Pi via Bluetooth, which means that in testing, I can drive this thing around and make sure, like if I'm manually controlling, so like typically it's autonomous, that's the hope. It drives itself around, but when it doesn't, there's some mechanism by which I can interface with this device and drive it around, give it commands and have it listen. So that's what the controller does, and it's over Bluetooth. The Arduino, yeah, and you can see the arrows are indicating information flow. So the skid steer drive system is two-way with Arduino, right? It's Arduino sensing and also giving actuation commands. The LiDAR and the camera are only supplying information to the Raspberry Pi. The Raspberry Pi is then communicating with the Arduino and the skid steer system. Yep, that's sort of the gist, I guess. That should be a two-way arrow. Anyways. Yep, what else? That's kind of the gist. I've got a wiring diagram next up. So the wiring diagram's fairly complete. So you can sort of see, right, there's a battery that supplies this system. It's a 12-volt battery that runs inside the autonomous mower's like control panel. And the 12 volts fused straight after the battery. There's an emergency stop button that sits atop the control system, so anyone can run over, hit a big red button and stop this system from running. The 12 volts gets converted down to 5 volts because the Raspberry Pi, Arduino, the control boards all need that 5 volts. Yeah. Everything else you can sort of see. I guess it's sort of self-explanatory to some extent. The controller is communicating over Bluetooth, so the BT on there is for Bluetooth. There's a Raspberry Pi 4, camera, LiDAR are both sitting on USB. The connection between Raspberry Pi 4 and Arduino is also USB. So it happens over serial, but yeah, the physical layer is USB. The two motor drivers, motor drive 1, motor drive 2, they are L298s. So they're like a very cheap little control board you can get, and they interface, they connect back to the pulse width modulation pins on the Arduino. In both cases, 5, 6 for drive 1, 9, 10 for drive 2. That signal from the Arduino is what is modulating the output of motor drive. So you can see the yellow and red lines that come out of each motor drive go to M1 right, M2 right, M1 left, M2 left, and they are, like I said, pulse width modulated 12 volts. So that enables us to reverse, change speeds, blah, blah, blah. And the whole system itself, like the whole mower, can steer. If we drive the right motor forwards and the left motor's back, we can turn left. And if we do the opposite, we turn right. So that's what a skid steer effectively is, or some people call it diff drive. So that like differential in rotation directions gives us steering. If they both drive forwards, we're obviously going forwards. If they both drive back, we're going back. And if we change one or the other, we're turning. That's skid steer. The encoders so there's only 2 encoders, one on each side of the mower. We don't need to get encoder positions off. We could and do some weird thing, but we're not. There's 2 encoders, one on each side. They come back to the Arduino's input pins, the appropriate ones. So D2, D3, A4, A5 is what I've used for that. They are providing like the encoder, every rotation of the motor, the encoder picks up some number of like clicks to some extent, sort of. So it's just this digital thing that's going up and down, basically, and picking up. So there's some mapping between like the rotation and the encoder thing, and usually it's quite high. So you get fairly precise measurements on like the wheel rotation, depending on the motor and how you set up the wheel, like diameters and stuff. Anyways, you can get feedback. It's basically the gist. You get feedback on the motor turns, and through that, you can get some sort of estimate of your position. And that's kind of like your global position. So you're like using the LiDAR, using the wheel encoders, you can sort of get position. So that's sort of the very fast rundown of the wiring diagram, you can see there's some extra wires there. The 5 and ground for the encoders, they just require power to work. So that's convenient that it's 5 because we already have that 5 volts running around for the Arduino motor drivers, Raspberry Pis. So those encoders and motor drives are sort of built on the back of like Raspberry Pi and Arduino voltages, right? Yeah, that's the wiring diagram. So there's a couple of communication protocols being used. ROS2 Humble is this like overarching middleware framework that I'm using because it really speeds up integration times. So you do have to learn this middleware. It takes some time to like pick it up, and to be honest, I'm not an expert at it by any means, but once you do, there's so many people already building in this system that like the classic open source stuff, someone's probably built it already, which means you can just like leverage their tools, right, and add to them. So that's sort of how this thing could come about reasonably quickly, is I'm utilizing this ROS2, specifically ROS2 Humble framework, which lets me do lots of like very complicated things because there's like stacks that have been built inside this framework for these types of things. So ROS stands for Robot Operating System. 2 is the second version. Humble's the latest release, and it's built on top of these protocols DDS, and DDS is like built on top of our real-time transport protocol system or something. So yeah, DDS is, like it says on the screen, it's like this open standard connectivity framework for real-time systems. So that lets us have this like distributed system, but still have a like, it's also secure. So it's like distributed system that is secure, and it's real time is like a little bit ambiguous, but anyway, they're calling it real time. It's very low latency. So ROS2 is built on this. So it's sort of becoming this like de facto standard in the open source community, ROS2 and DDS specifically. There was ROS1, a lot of complaints about ROS1 initially is like the lack of security and the lack of these like industrial protocols. DDS has really sort of addressed that with ROS2 Humble, and it's sort of moving into acceptance industrially. You can sort of look up like NASA, Blue Origin, these like Boeing, very large companies are starting to take notice of ROS2, and ROS2 is coming out with this new package called ROS2 Space, where they're really trying to address this industrial market. So they're trying to sort of move into become this like de facto standard for really industrial applications. So, which is awesome because there's a lot of really interesting applications already built in the open source community on this framework. So if we can get it sort of accepted industrially and build out its robustness to the point where like NASA, blah blah blah, are happy with the thing, then it's a really exciting time to be in like robotics and autonomous systems. So anyways, the whole framework is using this ROS2 like middleware thing. Then specifically, once you get down to it, the communication with from Raspberry Pi to Arduino is like a serial communication. The Raspberry Pi to the controller is using Bluetooth, and then there's like other little stuff. And yeah, I don't really consider like pulse width modulation a protocol. Maybe it is, but anyway. There's a few other little things, but anyway, it's more or less just like digital stuff after that, which is pretty much serial. So there's also like physical I/O. So like in the case of the cutting blade, where I'm switching a solenoid, I'd kind of call that like physical I/O, I guess. It's not really a communication protocol. It's just like I'm putting voltage on a coil and it's switching. So those are sort of the communication protocols. There's a bunch like the navigation stack is like the ROS2 Nav2 stack. The camera is doing object detection. That's a custom object detector I wrote. So yeah, that's not really a communication protocol, but I guess it is coding, and I'm not going to really delve into it. I've already gone like 3 times the amount over time, but in general, there's more to it, but yeah, these are the communication protocols. And there's this like requirement to talk about these three particular things in the rubric. So yeah, robustness, responsiveness, and real time. Responsive and real time is sort of like, yeah, I don't know. I consider them similar, like talking topics. But anyway, I've added security as well. So security in this case, I've already sort of talked about it. The whole framework for ROS2 Humble is built on DDS, and DDS is this like de facto standard for security. It's like you can go on. I've put it in the link. You obviously can't click it because this is a video, but DDS security is this like de facto standard. You can go and read about it. It's getting implemented in automobiles, space shuttles, airplanes, all over the place. That's the reason ROS2 Humble was built on it, because it was this accepted standard. In terms of robustness, ROS2 has these things called like quality of service settings. So you can sort of adjust the quality of service settings, which means that you're really flexible with how you demand ROS2 to work. So I've put a link there, you can go read about it, but basically my point about it is that ROS2 does address the idea of robustness, and these quality of service sort of settings are a mechanism by which you can have control over the robustness of your thing. So you can be very demanding about the robustness of your setup by changing those quality of service settings and yeah, ensuring that your particular build or whatever you're doing like does it. Responsive in real time. So this is like a very interesting one to me, because when people say real time, they typically just mean low latency, or they're talking about like determinism in their control system. And I still think there's some ambiguity. Real time to me depends on the situation, and responsiveness is just a general way of saying that. But anyway, so here's this. I've read this paper about ROS2, and this is quite interesting. I've gone way over time, but I'm going to just keep going over time anyway. So this particular graph, just to give you some context, is it's like they did a case study, right? And they're basically talking about this very specific package in ROS called MoveBase. And they're trying to, so MoveBase is like, it's like a planning algorithm, right? Like they're trying to figure out, they've got a global planner. Yeah, so they're trying to like move this thing around, right? It's like a pathfinding algorithm. They're trying to move some particular robot or whatever around, and they're trying to figure out like what's the worst case execution time for that to happen. So that's the gist. They've got this like path planning thing, and typically they're like quite poor performing, or anyway, you'd expect them to be longer. They take longer. So you can, I guess, what I'm really getting at here is like, this is totally relevant to the lawnmower, because it's exactly the type of thing I'll be doing, some global planning for navigation. And you can sort of see the latencies right on the screen, right? Like we're talking, yeah, what's the highest number on the screen? Like 200 milliseconds. It's like, it's really, really low for such a like high demand type activity. And I guess that's my point, is like real time is ambiguous, but we're talking on the scale for like this, for the absolute worst case of anything I can see on the screen, it's like 200 milliseconds. So we're talking like a really short time in order to do like navigation. If, you know, my robot is not going so fast that 200 milliseconds is going to be like too quick, right? Like there's no way I'm going to be able to spin the wheels so fast that the 200 millisecond latency in the path planning is going to have any effect whatsoever on me getting to the place successfully. Like it's so small relative to the relative to my application. 200 milliseconds may matter in some application. So this study was obviously like more careful than I'm being by just pointing out the maximum. But for my particular use case, it's totally going to be acceptable. Yeah, I guess that's pretty much the whole thing. Thank you for listening, despite me going 4 times the allowed limit.